There's a deeply ingrained belief I want to challenge. Not some obscure theory held by a fringe group, nor a simple misunderstanding from someone who never picked up a physics textbook. I'm talking about a concept so fundamental that engineers use it to design complex circuits, electricians rely on it to wire buildings every single day, and physics educators sketch it on chalkboards in classrooms across the globe. I'm referring to the idea that electrical energy flows through wires. The truth is, it doesn't. The energy in an electrical circuit does not journey inside the copper conductor. It does not travel alongside the electrons. When you illuminate a room by flipping a light switch, the energy that ignites that bulb did not embark on a journey from the distant power plant, traveling through the metal core of the cables in your wall. Instead, it traveled through the empty space that surrounds those cables, through the air, through the ambient environment, through the seemingly void region adjacent to the wire, never within it. I understand how counterintuitive this sounds. I'm fully aware that your mental framework for electricity almost certainly involves a current flowing through wires, ferrying energy from the power source to the device. I know that textbooks are filled with diagrams showing arrows inside the circuit lines, pointing in the direction of the current, strongly implying that this is the pathway for energy. Those educational resources are, at their kindest, radically incomplete, and at their worst, actively deceptive. The accurate understanding was uncovered in 1884 by the British physicist John Henry Poynting. It is a direct and rigorous consequence of James Clerk Maxwell's famous equations. It has been validated by every single experiment ever conducted on the transfer of electromagnetic energy. And it reveals a fundamental truth about the nature of fields, the essence of energy, and the true identity of what we call electricity. Even after dedicating half a century to working with electromagnetic theory, I continue to find this revelation utterly astonishing. Allow me to guide you through exactly what transpires when you activate a light switch. And I assure you, by the time we're finished, your perception of electricity will be forever transformed. Let's begin by outlining the conventional model, the one that's universally taught, the one that is incorrect, or at minimum, profoundly incomplete. Imagine you have a battery. On one end is the positive terminal, on the other, the negative. You connect these terminals to a light bulb using wires. In this standard picture, current flows from the positive terminal through the first wire into the bulb and then returns via the second wire to the negative terminal. Within this framework, electrons are the energy couriers. They collect energy from the chemical reactions occurring inside the battery and transport it through the conductive pathway to the bulb. Upon reaching the bulb, they relinquish this energy, which heats the filament until it glows. The now depleted electrons then journey back to the battery to be recharged, and the cycle repeats indefinitely. This model possesses a certain logical coherence. It aligns with our everyday intuition. Electrons are physical matter, and matter can certainly transport energy. Current is defined as the flow of electrons. Therefore, it seems logical that current carries energy. The fundamental problem is that this is not what actually takes place. Let's examine the evidence. Consider the issue of speed, the first significant clue that something is amiss. When you flick a light switch, the light responds almost instantaneously. The electromagnetic signal conveying the on command travels at a substantial fraction of light speed, typically around 2/3 of it for standard household cables. However, the electrons themselves within that wire are moving at an entirely different pace. In a standard copper wire conducting a current of a few amperes, the drift velocity of electrons, the average net speed at which they migrate through the conductor, is approximately 1 millimeter per second. To be absolutely clear, that's not 1 millimeter per nanosecond, nor per microsecond, but per second. To put this into a comprehensible context, at a rate of 1 millimeter per second, an electron in a wire would need about 280 hours, or nearly 12 days, to cover a single meter. If your local power plant is situated 20 kilometers away, and you subscribe to the idea that electrons are the energy carriers, it would take that electron roughly 600 years to make the trip from the plant to your home. Yet, as we know, your lights turn on almost instantly. The signal propagates at a significant fraction of light speed. Therefore, something is conveying energy at velocities approaching the speed of light, and that something is definitely not the electrons. This brings us to the Poynting vector. In 1884, John Henry Poynting published a paper entitled On the Transfer of Energy in the Electromagnetic Field. Within it, he formulated an expression for the energy flux of an electromagnetic field, essentially the rate at which energy flows through a given surface. This expression is now famously known as the Poynting vector. It is represented as S sur 1 m0 exb, where S is the Poynting vector, E is the electric field, B is the magnetic field, and m0 is the permeability of free space. The Poynting vector indicates both the direction and the magnitude of electromagnetic energy flow. It points in a direction perpendicular to both the E and B fields, and its magnitude is proportional to the product of their strengths. This is not an approximation or a conceptual model. It is an exact result derived directly from Maxwell's equations. The Poynting vector represents the actual energy flux of the electromagnetic field. Now let's apply this to a basic circuit, a battery connected to a resistor with simple wires. Current flows through the loop. What do the electromagnetic fields around it look like? Inside the wire, there exists a minor electric field aligned with the direction of current flow, which is what nudges the electrons along. This field arises from the potential difference along the wire's length. Crucially, outside the wire, there is a much more significant electric field that points perpendicularly from the wire, directed from regions of higher potential to lower potential. Additionally, a magnetic field is present. The flowing current generates a magnetic field that encircles the wire, as described by Ampere's law. This magnetic field exists both inside and outside the conductor, but it is most intense just beyond its surface. Now, let's calculate the Poynting vector in the space outside the wire. The electric field E is oriented roughly radially, pointing either toward or away from the wire, perpendicular to its length. The magnetic field B forms concentric circles around the wire. Their cross product, EXB, results in a vector that points parallel to the wire, precisely in the direction of energy flow towards the load. But pay attention to the location. The Poynting vector is significant outside the wire. The energy is streaming through the space that envelops the conductor, not through its interior. Inside a perfect conductor, the electric field is exactly zero, which means the Poynting vector inside is also zero. No energy flows within it. For a real-world conductor with some resistance, there is a minuscule Poynting vector pointing radially inward. This represents the small amount of energy that does enter the wire, only to be dissipated as heat due to resistive losses. However, the primary energy flow, the vast majority of power transferred from the battery to the resistor, occurs outside the wire. This is Poynting's revelation, a fact confirmed by experiment derived exactly from Maxwell's equations, and it stands in complete opposition to the mental image of electrons ferrying energy through the conductor. To make this visualization more concrete, consider a specific geometry, a long, straight wire. The battery is connected at one end and a resistor at the other. Picture the electric field lines. Far from the wire, they run roughly parallel to it, tracing a path from the high potential end to the low potential end. Closer to the wire, they angle slightly, developing a small radial component that points toward the wire's surface. This is the component responsible for driving current inside the conductor. Now, visualize the magnetic field lines. They form perfect circles around the wire, like concentric rings that are tightest near the conductor and spread out with distance. At every point outside the wire, compute the cross product. E is largely parallel to the wire, B is circumferential. Their product, EXB, points both radially inward toward the wire and axially along it toward the resistor. The resulting pattern shows electromagnetic energy converging from all directions, funneling in toward the wire from the surrounding field, and then flowing along the outside of the conductor toward the load. The wire is not functioning as a pipe through which energy flows. Instead, it acts as a guide, a boundary condition that molds the electromagnetic fields around it, channeling the energy flow through the space that surrounds it. This is an entirely different mental model, and it is the accurate one. The concept becomes even more explicit with a coaxial cable, the type used for cable television, radio frequency circuits, and radar systems. A coaxial cable consists of a central conductor surrounded by an insulating layer, which is itself surrounded by a cylindrical outer conductor, and finally an outer insulating jacket. Current flows in one direction along the central conductor and returns in the opposite direction along the outer conductor. Now, where are the fields? In a properly functioning coaxial cable, the electric field exists exclusively in the insulating region between the two conductors, pointing radially from the inner conductor to the outer conductor. Outside the cable, the electric field is exactly zero because the equal and opposite currents in the two conductors cancel each other's external effects. Inside the conductors themselves, the electric field is essentially zero, as they are good conductors. The magnetic field is similarly confined to the region between the conductors, circling the central core. Outside the cable, it's zero. Inside the conductors, it's negligible. Consequently, the Poynting vector, EXB, is non-zero only within that insulating gap. The energy flows entirely through the insulation, not through the metal conductors at all. This isn't a subtle effect, it's a blatant fact. The conductors in a coaxial cable carry zero net energy. The energy is transported via the dielectric insulating material between them. Engineers who specialize in coaxial cable design are intimately aware of this. The properties of that dielectric material dictate the wave propagation speed, signal attenuation, and the cable's power handling capabilities. The metal conductors themselves are simply boundary conditions. Perfect conductors would be perfect guides, but they would carry no energy themselves. Further evidence comes from the skin effect. Here's another piece of proof that energy does not course through the bulk of a conductor. At high frequencies, alternating current ceases to flow uniformly across the wire's cross-section. Instead, it constricts to a thin surface layer, known as the skin depth. At the standard U.S. power frequency of 60 Hz, the skin depth in copper is about 8 millimeters. At 1 megahertz, it shrinks to approximately 66 micrometers. At a gigahertz, it's a mere 2 micrometers. At such high frequencies, the interior of the wire is essentially devoid of current. Only the surface participates. Why is this? Because the electromagnetic fields cannot penetrate deeply into the conductor. The rapidly fluctuating magnetic field within the conductor induces electric fields, eddy currents, that actively oppose the penetration, effectively canceling the field in the interior. The fields, and therefore the current, are confined to a thin outer shell. This aligns perfectly with the Poynting vector picture. Energy flows in the fields outside the conductor and only enters it from the outside through that thin skin layer. At high frequencies, the penetration depth is minuscule. The fields only interact with the outermost atomic layers. The skin effect has massive practical implications. High-frequency signals must be carried by conductors with large surface areas, not large cross-sectional areas. Hollow tubes function just as effectively as solid rods for high-frequency currents because, in reality, no current flows in the interior anyway. This is the electromagnetic field announcing, loudly and unmistakably, that it is unconcerned with the interior. The real action is at the surface and in the space beyond. The argument reaches its logical extreme with the antenna. An antenna radiates electromagnetic waves into free space. Energy flows outward, away from the antenna, borne by the electromagnetic field. There is no physical wire stretching hundreds or thousands of kilometers to the receiving antenna to carry this energy. The energy traverses the vacuum, guided by nothing but the fields themselves. Every radio broadcast, every Wi-Fi signal, every cellular phone call, all of these involve energy transfer occurring through the electromagnetic field, with no conductor acting as a conduit. The fields are the sole transporters of energy. A receiving antenna then converts this field energy back into an electrical current, but the energy's journey was as a field, not as a current within a wire. Now, consider a transmission line, like two parallel wires carrying a signal. This is essentially an antenna that hasn't yet chosen to radiate. The fields nestled between and around those wires guide the energy from the source to its destination. The wires provide the necessary boundary conditions to shape the fields, but the energy itself flows within those fields. As frequency increases and the geometry is altered, the signal can begin to radiate away, and the transmission line transforms into an antenna. The physics, however, is continuous. The mechanism of energy transport remains, in all cases, the electromagnetic field. The wire is perpetually a boundary condition, a guide, a sculptor of fields, but it is never a carrier of energy. So, if electrons aren't carrying the energy, what is their role? They are performing an essential function, but it's different from the common conception. Electrons within a conductor respond to the electric field, and in doing so, establish the necessary boundary conditions for the fields. Their collective behavior, responding to fields, distributing charge on surfaces, carrying current, determines the precise shape of the external electromagnetic fields. Think of it this way. Electrons are the machinery that adjusts the field configuration. When you connect a battery to a circuit, the electrons in the immediate vicinity of the battery terminals instantly respond to the potential difference. They arrange themselves into a specific surface charge distribution along the wires. This surface charge, in turn, generates the electric field outside the wire, the very field that guides the Poynting vector toward the load. The signal propagates at near light speed, not because electrons are racing through the metal, but because alterations in the field configuration propagate at that velocity. When you flip a switch, a change in the electromagnetic field pattern radiates outward from that switch at nearly the speed of light. This traveling wave instantly reorganizes the surface charges on every segment of the wiring, creating the field pattern that will channel energy to the load. The electrons are akin to the water molecules in an ocean wave. The wave itself moves at its own speed, which can be quite fast, while the individual water molecules merely orbit in small circles. Energy and information travel within the wave, not through the bulk motion of the medium. In the same way, electromagnetic energy and signals travel within the field wave. The electrons are the medium that supports and shapes the field, but they do not carry the energy through their own sluggish drift. Let's be more precise about why the Poynting vector is the correct descriptor of energy flow. Maxwell's equations, the four foundational laws of classical electromagnetism, imply a fundamental energy conservation law known as Poynting's theorem. It states UT Ers S plus JE. In this equation, U represents the electromagnetic energy density, energy per unit volume stored in the fields. S is the Poynting vector, J is the current density, and E is the electric field. In words, the rate at which electromagnetic energy density decreases at a point equals the rate at which energy flows out of that point, the divergence of S, plus the rate at which the field does work on charged particles, JE. This is an exact local energy conservation law derived directly and rigorously from Maxwell's equations. It declares unequivocally that electromagnetic energy flows according to the Poynting vector S. If you wish to know the pathway of energy, you consult S, not the current density J, and not the electron drift velocity. You look at S, where's Gauss Adam Zau 0, EXB. This is not a model. It's a theorem from the most fundamental equations we have. One might ask if this is the only way to define electromagnetic energy flux. Mathematically, you could add any divergenceless field to S and still satisfy energy conservation. The Poynting vector isn't uniquely determined by energy conservation alone. However, it is the natural gauge invariant Lorentz covariant choice, and in every experimental situation where we can directly test energy flow through radiation pressure, antenna measurements, or circuit power transfer, the Poynting vector provides the correct answer. More fundamentally in quantum electrodynamics, the relativistic quantum theory of light and matter, the energy-momentum tensor of the electromagnetic field has a specific form, and its energy flux component is precisely the Poynting vector. At the quantum level, there is no ambiguity. The Poynting vector is the energy flux, period. Let's walk through what happens the instant you close a circuit. At time zero, you flip the switch. A wave of electromagnetic field change propagates outward from the switch at the speed of light, modified by the dielectric materials around it. This wave reorganizes the electric field configuration along the entire length of the circuit. Before this wave reaches a particular point along the wire, that point remains blissfully unaware that the circuit has been closed. After the wave passes, the field at that point is permanently altered. Before the wave's arrival, the Poynting vector at that location is zero, no energy is flowing. After the wave passes, the Poynting vector is established, pointing along the circuit toward the load. Energy flow has commenced. The energy does not wait for electrons to physically drift from the switch to the light bulb. The field wave propagates, reorganizing the field everywhere, and energy begins to flow immediately after the brief light speed delay. This is the reason your lights turn on so quickly. Not because electrons race from the switch to the filament, but because a field wave propagates at nearly the speed of light, establishing the configuration that channels energy through the surrounding space. The electrons in the wire between the switch and the bulb barely move. They oscillate slightly in response to the passing wave, maintaining the necessary boundary conditions, but they are not carrying energy from one point to another. The field does that. This field-centric perspective also clarifies a concept often poorly explained: energy storage in circuit elements. A capacitor stores energy. Where is that energy physically located? It resides in the electric field between its plates, not in the charges clinging to the plates themselves. An inductor stores energy. Where? It is contained within the magnetic field in the core and the space inside its coil, not in the current flowing through the wire. Energy is stored in fields. When you charge a capacitor, you are building up an electric field in the gap. When it discharges, that field collapses, and the energy flows out as a Poynting vector from the interplate region, through the surrounding space, to wherever it is being consumed. When you energize an inductor, you are establishing a magnetic field. When it releases its energy, the collapsing magnetic field induces an electric field, and their combination produces a Poynting vector that carries the energy out. Every energy storage element in a circuit stores energy in fields. Every energy transfer within a circuit occurs through fields. The wires and components are merely the apparatus that creates, maintains, and directs these fields. But the energy itself resides in the fields. Consider a piece of hardware that makes this field picture undeniable: the transformer. A transformer consists of two separate coils of wire wound around a common iron core. There is no electrical connection whatsoever between these two coils. They are electrically isolated, and yet energy is transferred from one coil to the other with remarkable efficiency. Transformers routinely achieve 98% or 99% efficiency and are ubiquitous in the power grid, used to step voltages up and down. How does energy leap from one coil to the other without any conductive path? It travels through the magnetic field in the iron core. The primary coil, powered by an alternating current, creates a changing magnetic field within the core. This changing magnetic field threads through the turns of the secondary coil, and by Faraday's law of induction, induces a voltage across it, which can then drive a current in a connected load. Energy is transferred from primary to secondary exclusively via the intermediary field. The electrons in the primary coil never interact with or even come close to the electrons in the secondary coil. There is no wire connection. Yet energy is transferred efficiently because the electromagnetic field couples the two coils. This is a macroscopic, everyday piece of electrical engineering hardware that operates successfully only because energy is carried by fields, not by electrons and wires. If the conventional model were true, the transformer would be an impossibility, a violation of energy conservation, requiring energy to teleport from one disconnected circuit to another. It isn't teleporting. It's flowing through the field, through the iron core, through the space inside the transformer's housing. The transformer is physical, tangible proof that electromagnetic energy is transported by fields. The same principle powers the wireless charging pads for your smartphone or electric vehicle. You place your phone on a pad with no plug, no metal-to-metal contact, and yet energy flows from the pad to the device. The pad houses a coil carrying an alternating current, which generates a changing magnetic field above its surface. Your phone contains a receiving coil that sits within this fluctuating field. The changing magnetic field induces a current in the phone's coil, which then charges the battery. Energy has been transferred through space, through the air, via the electromagnetic field, with no wires necessary. The field is the carrier. This isn't exotic or futuristic technology. It's a direct application of the same physics governing a transformer. It's a technology you likely use daily, and it demonstrates unequivocally that energy can transfer through fields without any conductive connection between source and load. If you still clung to the belief that energy flows in wires, wireless charging would seem miraculous. It is not miraculous. It is the standard, ordinary behavior of electromagnetic fields. The wireless case is not the special one. The wired case is simply a specific geometry of that same fundamental field physics. To be fair to the conventional picture, let's acknowledge what it gets right. The idea of current flowing through wires and carrying energy isn't wholly wrong. It's just incomplete. It accurately captures certain aspects of circuit behavior while missing the underlying mechanism. The drift of electrons is real. They do indeed drift slowly. This drift does carry a minuscule amount of energy, the kinetic energy of the moving electrons themselves. However, this kinetic energy is astronomically tiny compared to the total electrical energy being transferred. More importantly, the flow of current is absolutely essential for creating and sustaining the fields that do carry the energy. Without current flow, there would be no magnetic field encircling the wire. Without that magnetic field, the Poynting vector would have no B field to cross with the E field, and there would be no energy flow. The current is the source of the magnetic field. The potential difference is the source of the electric field. Together, these fields generate the Poynting vector, which is the actual mechanism of energy transport. The current and voltage are the inputs. The Poynting vector is the output, the real-world energy flow. So, you can absolutely perform circuit analysis using Kirchhoff's laws, Ohm's law, and power calculations without ever mentioning Poynting. These tools are effective. They provide correct answers for voltages, currents, and power dissipation, but they do not reveal where the energy is physically located or how it physically journeys from the source to the load. For the vast majority of engineering design, this is perfectly adequate. You don't need to know the fundamental physics of energy transport to build a functional circuit. However, for a genuine understanding of what is actually happening, for building a robust physical intuition that seamlessly extends beyond simple circuits to antennas, waveguides, optical fibers, and the entirety of modern electromagnetic technology, you absolutely need the Poynting vector picture. This insight that energy flows in the field, not in the wire, is far more than an interesting footnote about circuits. It serves as a window into the deepest structure of electromagnetic theory. Maxwell's equations describe the electromagnetic field as possessing its own energy and momentum. The field itself, not the charges, not the currents, is the fundamental physical entity that transports energy through space. Grasping this concept brings a profound coherence to all of electromagnetism. Radiation, the energy broadcast by an antenna, is simply a case where the fields detach entirely from their source and propagate freely. A transmission line and an antenna are not fundamentally different. They are merely different geometric expressions of the same field physics. Light itself is an electromagnetic wave, a self-sustaining, oscillating pattern of E and B fields propagating through space. The energy within a light beam resides in those fields. The Poynting vector for a light beam points in its direction of travel, with a magnitude equal to its intensity. This is obvious and natural within the field picture. It would be deeply mysterious if energy were instead thought to reside in some material carrier. The quantum theory of electromagnetism, quantum electrodynamics, describes photons as quantized excitations of the electromagnetic field. The field is the fundamental object. Photons are field quanta. Energy is stored and transported in the field. The field is primary. Charges and currents are sources that create fields, respond to fields, and act as boundary conditions for fields. But the energy, the physical quantity that does work, that heats resistors, that powers motors, that illuminates bulbs, lives in the field. Why, then, is this crucial concept not taught from the beginning? Let me be direct about a point of frustration. Poynting's result is not new. It has been known since 1884 and follows rigorously from Maxwell's equations, which were complete by 1865. There is no debate or uncertainty about its validity. It has been experimentally confirmed in every test ever performed. Yet, it is almost universally absent from introductory physics and engineering curricula. Students learn Kirchhoff's laws, Ohm's law, and circuit analysis. They are taught that current flows through wires and carries energy. Later, if they pursue advanced study in electromagnetism, they encounter the Poynting vector. And if they are thoughtful, they experience a jolt of realization that their foundational understanding was, at best, incomplete. Why this pedagogical gap? Partly, it's a matter of convenience. Circuit analysis is far simpler without the complexity of fields. Kirchhoff's laws are easy to apply. The field picture demands a grasp of vector calculus and an abstract conceptual comfort that introductory students typically lack. Partly, it's due to historical inertia. The conventional current and wire model was deeply entrenched long before the field picture was fully developed, and it became the default language for discussing electricity. However, I suspect the primary reason is that many who teach physics do not fully appreciate the radical departure the field picture represents from the conventional one. They may view Poynting's theorem as an interesting but arcane result about fields, failing to recognize that it fundamentally reshapes the very meaning of electricity. It means that what we call electrical energy is, in truth, electromagnetic field energy. It means that transmitting power is a process of guiding electromagnetic fields from source to load. It means the wire is infrastructure for the field, not a pipe for the energy. So, does any of this change how you should design circuits or build electrical systems? For the vast majority of low-frequency applications, standard power systems, audio electronics, basic digital logic, the difference is primarily conceptual. Kirchhoff's laws and Poynting's theorem yield identical answers for all measurable quantities like voltages, currents, and power. You can successfully design countless circuits without ever thinking about fields. However, at high frequencies, in RF electronics, microwave systems, and optical communications, the field picture becomes absolutely essential. You must think in terms of fields, where they are, how they propagate, where the energy flows. Waveguides, transmission lines, antennas, and optical fibers are all designed by focusing on fields, not electrons. Even the fastest digital circuits now operate at clock frequencies where field effects are critical. Maintaining signal integrity in modern processors requires deliberate consideration of electromagnetic fields, ground planes, and transmission line effects. The simple wire picture fails, and field thinking becomes a necessity. Furthermore, in understanding and innovating with new technologies, wireless power transfer, near-field communication, electromagnetic compatibility, field thinking is utterly indispensable. More broadly, understanding that energy resides in fields changes your entire perspective on the electromagnetic world. Every electric motor, every generator, every transformer, every antenna, when understood correctly, is revealed to be a field machine, a device designed to create, manipulate, and extract energy from electromagnetic fields. The wires are simply the plumbing. In conclusion, let me articulate what Maxwell's equations have been trying to tell us for a century and a half. Energy in electrical systems does not flow through wires. It flows through the electromagnetic field inhabiting the space around the wires. The Poynting vector, S, EXB, oriented perpendicular to both the electric and magnetic fields, gives the direction and magnitude of this energy flow. Electrons drifting within the wires move slowly and carry a negligible amount of energy directly. Their crucial role is to create and sustain the boundary conditions that sculpt the electromagnetic fields. The fields themselves are the energy carriers. This is not a mere theoretical abstraction. It is demonstrably proven by the speed of electrical signals, by the transformer, which transfers energy between electrically isolated coils, by wireless charging, by the skin effect, and by the entire technological edifice of radio and microwave engineering. The wire is a guide, a boundary, a constraint that molds the fields, not a pipe conveying energy. The field is real. The field possesses energy and momentum. The field is the primary physical entity. Charges and currents are the sources and guides for the field, but not the energy carriers. When you flip a light switch, a wave of electromagnetic field change radiates outward at nearly the speed of light, reorganizing the fields around every conductor. The energy then flows from the source, be it a power plant or a battery, to the load, the bulb or motor, through the electromagnetic field enveloping the wires. The bulb illuminates because electromagnetic field energy converges upon it from all directions, entering from the surrounding space, flowing inward through the glass and tungsten, and heating the filament to incandescence. It lights up not because electrons are rushing through the wire with little packets of energy, but because the field surrounds the wire and delivers its energy precisely where it is needed. That is the true nature of electricity, not electrons in pipes, but fields in space. And once you have perceived it this way, it is impossible to revert to the old perspective. The universe is replete with fields. They carry energy, momentum, and information. They are the medium through which all electromagnetic interactions occur. Charges create fields, and fields act on charges. But the energy, the physical essence that matters, resides in the fields. Maxwell understood this. Poynting proved it. Every subsequent experiment has confirmed it. Now you understand it too.